Hi, my name is Craig Sipes, and we took the mousetrap car project, and then we gave it a theme. We made it more project-based by calling it the alternative energy vehicle. And so the students were asked to make a prototype of an alternative energy vehicle, one that would replace gas-guzzling cars or other sorts of polluting vehicles.
Hello, my name is Angelique Broster, and I attend George Washington Preparatory High School. In my AP Physics class, we've been working on alternative ways for gas and energy for cars. So we came up with the alternative energy vehicle. Are you tired of driving your car with just one arm because you use the other to pay for gas? Well, ditch your gas guzzler and pick up an alternative energy vehicle. Now, it moved a whopping 0.30 meters. Its maximum velocity was 0.07 meters per second. Its initial acceleration was 0.07 meters per second squared, and its final acceleration was negative 0.07 meters per second squared.
Hi, my name is Marcellus Fleshman, and I'm at Washington Prep High School. How the mousetrap car works is the bar goes up, pull it back, the stick pulls down the bar, the string unrolls, the stick unrolls, and the car moves.
Ready, set, go.
It just has to be 5 meters.
Hi, my name is Evan Dvorak, and I teach physics at Jordan High School in Los Angeles. This is our kinematics unit. Students went through a series of investigative activities that led them towards the culminating engineering project where they had to build a mousetrap-powered race car. They ran experiments on their vehicle, they iterated through various designs, and finally they competed against their teammates in distance and speed. Prior to working with the mousetraps, we modified the design slightly to improve their safety. Students took foam and some pretty light string, shoelace actually, and wrapped the foam around the bar on the mousetrap to prevent any injury in case of that bar coming down on someone's finger. As a way of field testing our safety improvements, we allowed the mousetrap to snap down on the pencil and check the surface of the pencil for any dents. This gave us somewhat of a ballpark figure as to whether or not it would hurt our finger.
So for our safety, to make the mousetrap safe, we use string to wrap around the initial impact zone and also the bottom zone. And then we put a foam in between it, so it protects it. Because in the first test we figured that we needed an extra support.
As a way of tying in the real-world financial constraints on an engineering project, students had to maintain a budget. So every item that they used in their mousetrap car, they had to figure out the cost of it and withdraw that amount from their account, calculate a new balance, and let that figure guide their future design considerations.
And our budget was $20, and we bought 4 wheels, which totaled out to $3, and we bought 2 sticks, which totaled out to $1, and the mousetrap was $5, and the three woods that we bought were $3 as well, and 1 piece of the string to wrap around the mousetrap was 25 cents, and the foam was 75 cents.
In preparing for the actual build, students had to come up with blueprints where they figured out the dimensions of their vehicle, determined their constraints and their requirements for that subsystem, and then developed a plan of attack with their teammates to engineer that system appropriately.
For the mousetrap racer car, what we did is, well, basically you just need a car, first of all, the car, and then you have to, since it's powered by the mousetrap, you have to get the string, you have to tie it from the back wheels or whichever wheels is going to power it, and you have to wind it up, and once you let it go, as it rolls, the string will cause the wheels to roll and that'll make it move.
And then for our design, we use 2 wheels, a piece of wood, and 2 stabs to connect them. So pretty much we're gonna do an incision and place this one inside, and then we're gonna tie the string on the outside. So when it pulls forward, it's gonna drive the axle forward, which is gonna propel the car forward.
To build it, it was in partners. It was 2 people in a group, and well, it was complicated at first because it's just difficult. Like you want your project to be a one way, and then the other person wants it the other way. But I mean, it helps too because you guys have different ideas, and you guys can combine it and make it better.
I like working with materials because I'm a hands-on learner. I like to do stuff outside of the classroom instead of being inside the classroom bored, just learning from the book and then not getting to go outside and experiment. With hands-on, it's more interesting and I get more excitement towards physics and science in general.
Well, basically this experience, to me personally, I think that has enhanced my physics as much as my hands-on, because certain material that are provided to us, not a lot of schools can get, instead of just copying other kids or something like that, the kids actually learn more. And personally, that's why I love the hands-on activity that comes with this work, because physics is not only about mentally math and stuff like that, it's about hands-on everyday lives, because students go through this every day, but yet they don't know it because they don't try figuring stuff out.